Good afternoon and good morning to our guests from overseas who have joined us from Europe for this session to report on some of the very exciting developments over there. I hope you had a bit of a break there, and I was really looking forward to welcoming you all in Melbourne here and showing you a bit around the place with all the wonderful things we have to offer here in Melbourne. So all I can show you in this virtual session is really a typical physicist's office, which you can see in all its beauty and chaos behind me. My name is Thomas Cron. I'm the chief physicist here at Peter MacCallum Cancer Centre, and I'm your host for the next session, which is focusing a bit on the technology side and radiobiology side of our proton and particle world. I would like to start the session by introducing Jacinta Yap, who is presenting from Melbourne University on the particle activities there, has had a long association with a variety of particle accelerators all over the world, and now recently has developed also exciting capabilities in the context of medical accelerator facilities. So please help me to welcome Jacinta.
Great, thank you. So firstly, thank you to the organisers for giving us this opportunity to be able to present today. I'm actually giving this talk on behalf of my group leader, Dr. Susie Sheehy, who's unfortunately not able to present today. So this overview of the group has been recently tasked to me. So just a disclaimer that a lot of these slides are actually Susie's. If you have any questions or you want to know further details, feel free to email her or myself. And I think she's connected as well and can also answer through the chat. So as a group, we look at different areas of accelerator physics and applications across different themes. So today I'll talk about the particle therapy work that we're looking at. So our group is quite a young group. We started in March of 2019, so early last year, although at this stage that sort of feels like 5 years ago. So we want to be world leading in different areas of expertise, fundamentally by maintaining and establishing partners and collaborators worldwide, as well as here in Australia. So we want to engage in research and work across the multidisciplinary areas and industry as well. And we want to take ideas from simulations to experiments and then to reality. So how do we fit in the general context of the field? So I think most of our audience here today is more familiar with the clinical side. So in terms of medical physics, the clinic mostly works with existing technologies. So a lot of the research and development is primarily application and facility focused. So you would optimize for treatments and the type of outcomes that you want to achieve based on the capabilities of your fixed technologies. So the changes to the beam and delivery are typically done downstream in the treatment room itself. So in accelerator physics, though, we look at this from the other side, so behind the shielding wall in the accelerator bunker, and we want to change the starting point and bypass the limitations that are imposed by current technology. So to identify the challenges that are related to accelerators and any solutions and improvements that can be done by answering accelerator physics questions. So we want to change the game by creating alternative and improved approaches, so specifically to develop novel technologies to deliver particle therapy better. However, to do this, though, it's really important to establish as well as maintain this strong interconnection between these two fields. And this will be highly beneficial and important in terms of the progression of the field and future developments. So our group currently looks like this. We've grown pretty substantially in the first 18 months. We have a master's student, 4 PhD students. Myself, I started 2.5 months ago in October, another postdoc. Of course, our group leader, Susie, and 2 academics. So starting with the Bragg peak, of course, we know that comparatively X-ray photons and versus heavy ions and charged particles, heavier ions have a better dose distribution that's possible due to the Bragg peak. But of course, the characteristics of this dose deposition and the Bragg peak itself are determined by the particle type, so the intrinsic properties of the particle and the interactions. So typically with heavier ions, you have a sharper Bragg peak. There's less scatter. There is some fragmentation after the Bragg peak in the distal region though. So protons are easier to deliver, but we know that heavier ions can do more damage and have a more detrimental effect on DNA. Of course, protons are easier to deliver. The heavier you go, the more complicated it gets, and the more technical limitations. In terms of how this translates from physical dose to biology, it's quite complicated. But in general, due to the increased concentration, complexity, and occurrence of the strand breaks, we know that it's more difficult to repair. So therefore, with heavier ions, you have a higher radiobiological effect. So there is now a push into heavier ions and different particle types. But of course, this means that the next generation facilities needs to have machines that are smaller, cheaper, and faster to operate. So our group is actually involved in the NIM study, which is a collaboration that's led by CERN. This falls under the umbrella of the CEIST project, which is a big European project in the Balkans region. And the idea is to design next generation hadron therapy machine. So in terms of the accelerator design, this is two designs for a synchrotron, a normal conducting and a superconducting machine, both with the same beam parameters, however, with capabilities for advanced features. So sort of things that were identified in recent years as the minimum or now the idealized requirements that we want for future particle therapy treatments. So this includes different particle types like helium, carbon, and argon, as well as different extraction schemes. So Frank is a PhD in our group who's working on these designs. So we want something that's smaller and cheaper to operate and build, specifically designed for proton and carbon ions. So again, with different ion species, high beam intensities, and especially capabilities for these new emerging techniques as we move into the flash regime and with rapid scanning. So these capabilities sort of drive work into other areas as well. So our group is exploring MRI-guided proton therapy as well as multi-ion therapy with different collaborators. Again, even if you have a more advanced accelerator, you still need a way to be able to deliver this effectively and with the capabilities. That's not really done with current beam delivery systems. So the work that I've been doing recently has been looking at the entire process of the beam delivery. So we know that the availability and accessibility of particle therapy is largely limited due to the high costs and technological limitations. So in terms of the treatment time, this time is determined primarily by the efficiency of the beam delivery system. And it's been identified that the largest time contributor, or the limiting factor, so what takes the longest time in the whole process, is to actually change the beam energy. So to change the beam energy in depth when you're irradiating the different layers. So a potential solution for this is by using a large energy acceptance beam delivery system, using what's called fixed field alternating gradient optics. And in current facilities, there are lots of different methods that are implemented in order to switch between energies and sort of to circumvent the long time it takes to modulate the energy. So currently times range from anything between 100 milliseconds to seconds. So this, of course, is dependent on your facility, the type of accelerator you have. You can do this with a synchrotron. With a cyclotron, you need to actually physically put things into the beamline to degrade the energy. So especially with moving organs and with the respiration cycle, you need to be able to deliver a treatment very quickly. So at the moment, this isn't adequate. You need to be able to deliver much, much faster, so more than 10 times faster. A large energy acceptance beam delivery system has the possibility of achieving this because you're able to deliver multiple beam energies using the same parameters of your magnets. So this means that you minimize the time delays involved with adjusting certain things in your beamline, such as the magnetic settings. And this is especially important as we move to faster and higher dose rates, such as with flash. So there's a range of other benefits that can be possible with this. And this sort of drives emerging and new techniques with particle therapy and sort of we go into how proton therapy and particle therapy as a whole will look like in the future. So how do we do this? So firstly, with a design study. So we have a master's student, Elodie, who did a design. And in this picture here, you can see that basically based on this design of 2 different magnets, you're able to transport multiple beam energies. So this now can be built as a prototype, so a scaled down version in our lab. This design can actually accept energies within 0.5 to 4 MeV using the same single magnetic and optical configuration. So the idea is that we want to have this flexible system where we can test other concepts in hadron therapy from our lab in the University of Melbourne. We also have 2 PhDs in Manchester who are both working on particle therapy related projects based off this FFA technology. So this is great because we can combine the expertise from the University of Manchester and the Cockcroft Institute with what we have at the University of Melbourne with Susie. So a lot of this work is based on the stuff that Susie's been doing over the past years, as well as from her PhD. So Susie's involved in other things as well, so bits and pieces of outreach, as well as designing a course for school students and the new master's program at the University of Melbourne, and of course her book launch, which will all happen next year. So in terms of international activity as well, our group has just joined the Optimization of Medical Accelerators, or OMA network, which is also something that I was involved in during my PhD, which is basically a big European funded network that spans across all of the major particle therapy facilities in Europe and other research institutes, as well as some other partners around the world, such as in the US. So it's very exciting times. We've sort of glimpsed at the future of how radiation therapy using charged particle beams can look like. There's many different aspects of the entire workflow that can be improved. So limitations and things that can be made better, which are driven from developments from the accelerator side. So we are the first of our kind in this region. So we're the first academic accelerator physics group in Australia. So we don't just do particle therapy and medical applications in terms of accelerators, but other things as well. And it's really just the beginnings of this accelerator ecosystem and all of the capabilities that we want to grow and expand from our region here in Australia. It's very exciting, especially with the push with the Centre for Accelerator Science with ANSTO. Lots of exciting things to come. So we do have a lot of national and international partners and collaborators to continue to grow and expand on these capabilities. As a group, we want to contribute to the field and the emergence of particle therapy in Australia. So lots of work to do, but many things to look forward to. So keep watching this space. Thank you for listening.
Thank you very much, Jacinta, and also for a wonderful presentation. And thank you also for stepping in for Susie at very short notice. And by the way, gute Besserung for Susie. Just very quickly, you mentioned Flash, and obviously we here at Peter Mac are very excited to have an accelerator group right next to Peter Mac at Melbourne University. Do you think Flash will be an integral part of all future accelerator deliveries?
Yeah, so I definitely think so. It is a very new area of research and work. I think as we sort of come to understand the biology more, that will sort of develop more the areas that the accelerators and the technology needs to move into. There's definitely a lot of promise. If we can deliver fast treatments, then we can deliver more effective treatments.
Thanks again for a wonderful presentation and sort of really stacking that field for this session very nicely. The next presentation is by Simone Richter, and Simone comes from ANSTO and will pick up where Jacinta left it off by talking about research at large accelerator facilities, and we'll focus on value for money, something which is obviously very much in all of our mind.
Thank you, Thomas. I hope you can see my screen, or at least see me, so that's great. And Jacinta, it's been a great presentation and a great segue actually into my talk. And you noted I'm representing ANSTO here at LucasCytes, and in the background behind me you see a part of the Center for Accelerator Science, where we do use our accelerators here, do exciting things in environmental research or research into space applications, where we look into radiation hardness of electronics. And the beamline in the back to me are actually doing this work, or the scientists using those beamlines. So definitely for me, with a big accelerator background in my career, I would actually exchange the question mark by an exclamation mark. It is definitely value for money, and I hope you all join in my assessments at the end of my talk. So if we talk about accelerators, and there's a huge application in industry for accelerators, from ion implantation to better produce superconductors, electron beam welding, that really creates durable, high-quality welds for quite specific applications. Is really important in our new industries. And sometimes you count industrial accelerators, also those cyclotrons who are producing predominantly PET isotopes, and you see on the right-hand side our 18 MV cyclotron here at ANSTO at Camperdown in the centre of Sydney. So industrial accelerators are widely used, and if you, we still, I think, all remember going through airports and our baggage being screened. That's an accelerator as well that we use. So they are crucial to border security. They are used for waste treatments, not only normal waste, but also tapping into nuclear waste. They will be used for pollution monitoring, sterilization, as I already said, ion implantation, so non-destructive testing. You see just on the courtesy of the ENLIGHT collaboration, a summary of the over 3,000 particle accelerators that are in operation worldwide. Only the smallest part is actually used for research. And there's a tiny part of those accelerators that are looking into particle physics and nuclear physics, where we really need the large applications and the large accelerators themselves. Roughly a third is used for medical applications, and then the remaining 60% of all accelerators globally are in the true industrial applications. So not forgetting that in those good old times, some of us in the auditorium might still remember, every TV set actually was a particle accelerator over the with the tube where the electrons have been accelerated then to paint those beautiful pictures on the TV screen. Now with LED, we are having actually even less accelerators around us. Where do we come from? And accelerators are dating back many, many decades, and you see here depicted the first one at Oxford University in '48, getting a Nobel Prize. Now, where are we using those type of applications? Again, ion implantation, electron microscopes, high voltage for photocopiers, ionisers, X-ray tubes, name it, and I think you can almost link it back to particle accelerators. So it's a huge use of all the knowledge that has been generated into modern applications. If we further go down the pathway of the further developments around linear accelerators, or LINACs for short. Definitely there's the radiotherapy LINAC, which is the largest application of accelerators in the medical field, but we can also use it for other things, and they're usually used to pre-accelerate the particles for injection into synchrotrons, or actually be forming an X-ray free electron laser, where we currently have more applications into basic and fundamental discovery research, but because they are still new, but in 10, 20 years we'll actually see applications for them. And again, linking back to radiotherapy, the first patient has been treated in 1992. If you don't want to just build large, long accelerators, you can wipe them up. And that's the idea of the cyclotron. So the next step of larger scale accelerators, and here we are talking about a 27-inch that you see depicted on the right side, whereas then later on I'll shortly talk about CERN, where we actually talk about 27K circumference. So it's really all across the scaling. And again, huge impact on radiotherapy and particle therapy, as a synchrocyclotron was used in the late 50s, first time for helium-ion therapy. And today, those are the machines that are heavily used for creating PET isotopes and proton therapy. We climb further up the energy scale. We come up to synchrotrons, where we have access to the real high energy beam. And again, it's technology out of the late 50s, 60s. And they are still as new as of today. They are still operating. So coming back to the question, value for money, it's a huge investment upfront, but it's actually a long-lasting investment, and the outcomes and the outputs are still high with those old machines. And now we have roughly over 100 synchrotron light sources worldwide, from pharmaceutical development to energy materials, doing cultural heritage studies, and so on. So it's not only the industrial applications, also the societal impact, and branching out into other disciplines where we do enable, with the use of accelerators, other types of research. If we talk about modern synchrotrons, and you see Australia's largest accelerator down in Clayton near Melbourne, so again, close to the Peter Mac, the Australian synchrotron, and you see also a glimpse into the CERN accelerator LHC wing, and depicted the whole 27K synchrotron. If we talk about what does those machines bring into the value generation, it's actually the application of high vacuum. All those tubes that you see on the left corner down, they are under vacuum and high vacuum, sometimes even more pure vacuum than you would find into the intergalactical space. So you really bring it down to a pure vacuum. There are superconducting magnets that really push the achievable and the buildable things really out to the next generation. We learn about computer controls of all those elements along the way. We'll tap into machine learning. And if I talk about superconductivity, you need cryogenics. So it's also pushing into cryogenics and actually building those large accelerators like at CERN. It's also you're pushing the boundaries of what you can do in a civil construction and a technology sense. So even so, it's not visible and linked immediately to an outcome of the research done at those large facilities, which is more aimed to fundamental research. it has an immediate impact on industrial applications. With this audience, I definitely preach to the converted, and we talk about particle therapy, so it's just a glimpse how they look like, but it's what we do as our daily bread and butter, or what we hope will become daily bread and butter for the Australian context. It's actually using accelerators for particle therapy. And if we now come to one example of a large-scale accelerator like CERN, and the slides are courtesy of CERN, it's really linking particle physics and innovation. You never know where a technology can link into a real-world outcome that is there for the society. So from accelerating particle beams, detecting particles, you might actually invent the large-scale computing grid at CERN. And can we imagine a life without the internet or the World Wide Web? It's now in its 31st year, and it's a great technology. It goes from strength to strength, and it actually brings us together today in that virtual conference, and that was a byproduct of accelerator research, so to say. If we go further down into the medical application, actually the particle therapy and the hadron therapy is a spin-off of the particle physics. So now we see more and more patients being treated with hadrons, and because that is actually the better way, as Jacinta discussed earlier, better than protons, better than photons, if you actually want to access a deep-stated tumor. So we see that led out of the European continent and Japan, and hopefully we're pretty soon hosting the first proton therapy down in Adelaide, and hopefully a hadron therapy as well. So from proton therapy accelerators, you build synchrotrons dedicated to the application, and Jacinta was already talking about the studies at CERN, where the group of Susie is actually part of, and we do see facilities built after all those theoretical work done there, talking about the next study, the next step for particle therapy, and I'm running shortly out of time, so I'm really coming to an end. The next generation of accelerators, which CERN is looking into to build a new linear accelerator, not a circular one. Australia was, and the University of Melbourne is setting up a laboratory to host a small part of what's actually happening at CERN and looking into what we can learn for that. And there's a new treatment option that is currently under investigation and in modeling around very high energy electron therapy, where we go back to the electrons, the lightest particles, and combine them in two different energies for the application that will provide an even better painting of the tumor. So the journey with accelerators is not coming to an end. So the journey of the applications, and not only in the medical space, but in the industrial space and the spin-offs, are not coming to an end. And I hope you agree with me that accelerators are worth its money, and they are value for money. Thank you.
Thank you so much, Simone, for an absolutely fascinating look into a fascinating world of accelerators. For a physicist like myself, this is really a wonderful thing to look at. I'm just looking for questions, but while I can remind everyone to use the chat function for questions, I have a question because we are using so many accelerators in medicine. 30% of all of them are here. Could we use them at night for something else? Are there applications which would allow us to add value to these accelerator fleet? Also possibly for protons more than for electrons on our small scale in accelerators.
Oh, definitely, Thomas, definitely. And with my history at the Helmholtz Center for Heavy Ion Physics, and building up and working together collaboratively with the colleagues at Heidelberg, they are swamped with researchers coming in during nights and sometimes over weekends to use the facility, because it's a great access and it's a great asset for the research community outside the medical applications. And if we have identified for Australia that space is one of our growth opportunities, you need to test radiation hardness. So you're already coming from looking into the impact of ionizing radiation on living matter if you treat a tumor. So you can use the same things to actually look into, for example, radiation hardness of electronics, which is important if you send it up to space. That's an interesting field. There's definitely the colleagues that come from a more traditional nuclear physics background that can do experiments at night. So that's the great push within our national approach, that if we will get a hadron therapy, especially because the heavier the particles, the better for those types of research, we want to have a research facility that can serve multiple purposes, not only the medical and the health research, but also research into other areas. So yes, I think we'll see a big run onto those facilities.
This is certainly a very exciting future you're painting there, and I think for this community, something we do need to consider. You also showed a slide of the MEDAUSTRON facility, and that's a perfect segue into the next presentation by Dale Prokopovich, who has joined us from Vienna at a very early hour. So I don't want to keep him too long. He's going to talk about the MEDAUSTRON particle therapy facility, and I very much look forward to what he has to say.
Okay, thanks very much for the introduction, Thomas. So I'm going to be discussing today the MEDAUSTRON particle therapy facility, which you've actually seen in a few presentations today, various photos of it so far, but I'll give you a bit of an overview. So just to start, if you haven't been here or visited MEDAUSTRON, we're actually located outside of Vienna in a city called Wiener Neustadt in the state of Lower Austria. And this is a facility that is, you might have seen that there was sort of 12 carbon ion centers in the world, but only 6 of those can actually do proton and carbon together. And this is one of those facilities. So if we're looking at, because this is sort of a very cutting edge facility, and it's actually quite international. So apart from it just being like a national, like in Austria facility, you're actually looking at it, it's got 210 employees from 20 different countries working here. And it's required to maintain that sort of cutting edge technology that's being developed here. So this is a bit of an overview of how the MEDAUSTRON facility looks like. So if we're looking at, we'll start with the ion sources. So at the moment we have 2 operational ion sources. If you're looking at the proton and carbon ion sources, so that's for patient treatment and research. And there's currently in the process of being commissioned a 3rd ion source for helium ions, and there's a 4th branch available for future expansion to other ions, other heavy ions. So as you might have heard from some of the previous talks, that interest in sort of even moving to heavier ions potentially. So that then goes through this pre-acceleration stage into the synchrotron. So there's been discussions earlier about synchrotrons versus cyclotrons. Here we have a synchrotron-based facility, and this is then accelerates the particles up to the energy required, then transports down this high-energy beam transport line to the various treatment rooms. We have 4 irradiation rooms here at MEDAUSTRON. The first one here is specifically for research, and I'll describe that in a little bit more detail later. And then we have 2 fixed beamline rooms. The first one is a horizontal and vertical beamline,